Hey, everybody. I'd love to introduce Egemen Kolemen from Princeton, who's been working at this intersection of simulating plasma physics and machine learning. Welcome.
Hello. Hi, everyone. Egemen Kolemen from Princeton University. I'm a faculty at Princeton and at Princeton Plasma Physics Laboratory, which is a Department of Energy lab. So I kind of do both areas. So this is our group, and I'll talk a bit about what we do on the machine learning side for fusion. So first of all, you don't know fusion that much, so let me try to explain. Fusion is the main source of energy in the solar system, in our solar system, and in the universe. It's basically gives the energy that we need for wind. Wind is basically conversion of sun's rays into gradients of pressure that turns our wind turbines. And even fossil fuels are just stored energy from fusion from a million years ago. So what we try to do in fusion energy is to convert fusion into electricity or hydrogen directly. So that's the main thing. We want to put sun in a box, in a small box, as small as possible. So that requires us to do fuse particles. So you probably heard of fission, which is separation of big atoms. So you have uranium, you split uranium up, and you get energy. Fusion is the opposite of that. When you have very small atoms like hydrogen, you bring two hydrogen atoms together and combine them, you get energy out. So what you get is basically, these are the isotopes of hydrogen, deuterium and tritium. You combine them, you get helium plus 17, 18 MeV energy. So there's a lot of energy. And the nice thing about it is that you don't need you just need water, basically. There's enough deuterium in water. And so how do we do this, though? So in sun, everything is great because it's so big that gravity kind of compresses this gigantic plasma ball that is the sun. And this compression leads to the fusion happening because you need the particles to hit each other and not just run away. Obviously, that's a bit unpractical if you want a small size sun. So what we try to do on Earth is to use magnetic fusion, magnetic confinement. So here you have a magnet. This is the south. This is the North Pole. So you can have a magnetic field like this. And what happens in a magnetic field is if you have ions and electrons, which is the case when you have very hot plasma. So when you heat things up, they become solid to fluid and then fluid to gas. And you feed them really higher, that just becomes plasma, which is just electrons and ions just flying around. So these electrons and ions, they gyrate around the magnetic field. So they're confined. That's perfect. So they don't fly off in this direction. But at the end, they hit the magnet here. So this is not perfect. So you lose the hot plasma at the end. So you can do a better job by turning this magnet and turning it into a donut. So this is what the Russians did in the 50s, and it's called tokamak. So you have plasma here, this yellow thing, and we have magnets outside of it. So these magnets make the magnetic field so that electrons and ions are just stuck in that donut. They don't go out. And we heat this up, and then it fuses. That's the idea. What is the state of fusion power? This is the fusion power in megawatts versus years. So we made a lot of progress, and by 2000 we were able to get to tens of megawatts, and achieved 70% of input power turning into fusion. So that's great. And you probably heard of the inertial fusion guys. They just got to more than one input energy to conversion into fusion. So what is next? Next is we kind of know what to do in simple ways. We want to build a reactor. The machines that we had were, test reactors. They're a bit small. We are building ITER. This is this international collaboration between US, EU, China, India, Russia, and Korea. And it is the largest research endeavor that humanity has ever taken. It's bigger than CERN by orders of magnitude. And hopefully this will help us on the path to fusion energy. This is going to produce 500 megawatts of power by putting 50 megawatts of power. So it's going to get 10 times the input power. And it will prove that fusion can be a source of energy. And it's finishing within the next decade. And then there's obviously the fusion private companies that started up within the last 5 to 10 years. And these fusion startups are, there was one or two back in the day, but it exploded. Now there's about 50 of them and billions of dollars being invested. These are some of the companies. And we do work with some of these companies. I work with about maybe close to 10 of these companies, help them out with some of our software, some of our analysis, controls, etc. So, hopefully the combination of ITER and the private companies will get to fusion energy production soon enough. So what do I do? I'm a professor, so we do a bunch of...
How different are the reactor designs from each other? Like you said, like NIF versus tokamak versus stellarator, and how many more others?
Okay, so the magnetic fusion, let me just see. This is not coming up. There's no like a text that's coming up, right? You're just asking it on the personally. Okay.
No text, yeah.
Okay, so the tokamak is this donut-shaped one. This is the standard one. I would say standard in the sense that this is the closest to breaking even on a reactor level. So that's why when we talk about fusion, magnetic fusion, this is what we kind of focus on. There is another one that I can show. Oh, there's an example here. It's a stellarator. It's a bit like a 3D shaped, it's like a French coroller instead of a donut, if you will. This is another magnetic fusion reactor, but these are a bit further out. We work on those as well. But if you look at like a tokamak here, another tokamak, they kind of look alike. And then there is non-magnetic fusion, which is mainly inertial confinement. So what inertial confinement people are doing is you need a lot of energy for confinement. So what they're doing is they're basically hitting a target very fast with a hammer. There's basically people who are doing like you smash into it, and then that smashing energy converts the hydrogen in it and allows it to fuse. There's a third one, which is what you heard in the NIF, the National Ignition Facility. There's laser-based confinement. So what they do is they have a bowl, literally a bowl. You put huge amounts of laser energy on it, and this laser energy collapses this bowl. It's a golden bowl. And when it collapses, that pressure buildup allows you to fuse. Those are the three. I didn't have a slide on this, sorry, but those are the main types.
Thank you.
Yeah, but realistically, the one that's closest is magnetic fusion. It's the one that's closest to becoming a electricity production reactor. So that's why I'm focusing on that. Okay. So we work on different machines in Korea, in US, and everywhere, and we look at different things. I'll talk a bit about what we do on the control and machine learning side. So before we get started, what is the main issue that we have in a tokamak? I'll explain that. So this is a tokamak at CMOD. It was at MIT. So you see the plasma being formed now. So what you're going to see here is that as the plasma is forming, this is a camera that's looking at the visual. You're not seeing the inside because the inside is so hot that it's radiating an X-ray. So you're only seeing the edges of the plasma where it radiates invisible. And then all of a sudden, the plasma just disappeared. So what happened? I'll go back here. So, okay. So what happened is that there's fireworks all of a sudden. So this very fast disruption of the plasma ended up hitting the wall, and you see these fireworks are basically metal pieces flying and radiating away. So this is a big problem for tokamaks, this disruption, and that is one of the main challenges that we try to solve and make it stable. So this is what this is a motivation. So how do we kind of make the plasma stable, the fusion reactor stable? So this is the tokamak, and this is the plasma inside, the yellow. And this is a stable plasma. It can become unstable in seconds. It becomes unstable like this. But the problem was once it gets unstable, the growth of these instabilities afterwards is millisecond level. It's very fast. So it's very hard to control, almost impossible in many ways. And that leads to the plasma hitting the wall, where I showed the video of. And then you can melt the wall, break the machine, and so forth. So this is an example from jet reactor. And we can't handle this in either. So how do we avoid this? So as you see, we have to avoid it from the beginning. So we can't have unstable plasma, because if we do, then it's very hard to control afterwards. So once we avoid becoming unstable, then we can avoid the whole sequence of these things. And to do this, obviously, you need a real-time, fast machine, a cluster running in real time, doing analysis of the plasma and doing controls. So this is the main motivation. For this, I've been leading a big collaboration, multi-student collaboration with colleagues from Princeton, PPL, SLAC at Stanford, Carnegie Mellon University, and Wisconsin. So here what we do is we have all these diagnostics, real-time sensors. We analyze them at the edge, EgeML, because there's a lot of data. And then we predict what's going to happen to the plasma. And then we design control systems. And then we act with our actuators, like beams and microwaves. So the way to think about control is kind of think about it as we have this desired input, and we have the hammer, that's our controller, and the plant is our fusion reactor, and we have the measurements, that's our eyes. So I'll talk about how we can think of the eye and do the ML with the eye part, and then the control part, and how to combine it together. So we have a lot of diagnostics in current reactors. This is D3D. You'll see about there's probably dozens of diagnostics here. So electron cyclotron emission imaging, there's reflectometer, all sorts of things. So we can measure densities of ions and electrons and temperatures, etc. But that will not be the case when we go to a reactor, because reactor is a nuclear environment. You can only have minimal diagnostics, and nuclear environment means there's going to be faults and failures. So when we go from current reactors to either to a demonstration reactor, how can we make this robust with minimal diagnostic stakes is a very open question, hard to do. And we think we can use machine learning to do this. So first I'll tell what is the state of the plasma. So we have to first find the state of the plasma and see if it's stable or not, right? That's the thing. So state of the plasma can be simplified to the shape of the plasma plus 1D profiles. So what do I mean? So this is the plasma cross-section. When I say the shape, I'm talking about these nested surfaces. These nested surfaces are where ions basically are gyrating around. They kind of confined to these surfaces. Finding the shape is number one. And then once you have this, because the cross transport along this is very high, so you basically, if you know the temperature along this line, the temperature along everywhere is kind of known. So we need these 1D profiles from zero, the core, to the edge. So we basically say that we can know 6 parameters, 6 profiles, like the pressure and the current and the densities and temperatures, and the shape. That's our state. So how do we find it? So the shape one, we have a PDE, partial differential equation. This is a very nonlinear PDE, but it is a PDE nevertheless. And what we do is this tells us the equilibrium state given the profiles and the shape. But what we need to do is, given the diagnostics, like Thomson scattering here, charge exchange, all these other diagnostics, we do a fitting process. So we fit the best equilibrium that satisfies this PDE to these diagnostics, right? So that's called the real-time equilibrium fit, RTE fit. So this is great. We have some code that does this, but it's a very nonlinear PDE, so we have like a very simplified version of it that runs in real time. And so this is the current system, if you will. You have the machine, the diagnostics, control system. Diagnostics goes into a simplified physics model immersion, and then you get the profiles and the state. What we did initially was to do a surrogate model. You know, machine learning is great for surrogate model. I'll come to more exciting stuff too, but just getting started here. So basically, we take that physics model and convert it to a machine learning-based immersion. So how do we do this? We take the inputs to our PDE, and we put the outputs to our PDE, and we fit a neural net to that in simplest ways. And we call that equilibrium net, EQ net, and it's much faster, and it's much more robust, which I'll come to in a second. So we can run this very fast in some milliseconds. So you say, okay, I took the PD and made a neural net version out of it. What do I gain? Well, first off, we can show that you're getting the exact equilibrium that you would have got offline when you do the very slow calculations, not the real-time simplified calculations. This is the offline versus online. They're basically on top of each other. Second, I can run this extremely fast. Neural nets, we can run them very fast. So I have, in the real calculations that we do, when we did this, we compared to the physics-based models that's running real time, I introduced roughly 5 milliseconds of delay. So this is the simplified physics model that was running on real time, the red one. And the red and the blue and the yellow are neural nets and offline calculations. So I can get rid of this time delay, number one. And number two, because I'm doing the full calculation, I can get rid of this weird issues. Sometimes when plasma is changing too fast, the simplified solution doesn't work. So this is what you get. You get this. This is a real shot where you get like a bean-shaped plasma as calculated using the simplified physics model. Obviously, this is not correct, and the correct version is this. But when you do get a bean-shaped plasma like this, plasma instantly dies because you're taking control action based on this very wrong equilibrium. And because your calculations are fast, you can act much faster. And if you know controls, if you're fast in control, you can control much better and stably. So this is what this is simulation of NSTX with a neural net control. What we are able to do is, because we're getting rid of the time delays, we can make a very unstable plasma stable. So this is the highest elongation. Elongation is basically the height from here to the bottom. And the higher the elongation, the better fusion performance. You can get much better confinement. So we are able to achieve this using a neural net's surrogate model. Okay, so this is number one. Is that a question?
One more question. Yes.
Yes.
So obviously it's faster, but it also has a gradient. Is that something that helps you find, like, invert the model?
That is right. So we do get the gradient. I did not talk about it here, but so what we do is I even skipped it. So once you have the neural net, like you said, we have the gradient, and the gradient allows us to design the pertinent here, which allows us to design the control, right? So that is a big gain there. So I don't only get the F, right? That maps me from X to Y. I get df/dx. And right. I do need df/dx to do the control. Voila. So okay, that's basically coming for free. And that's how we are able to do the control design. So
thank you.
Yeah. So this is great. This is very useful, but this is kind of the stuff, everyone knows, if I have a map that takes me from X to Y, I can do a surrogate model. This is kind of known. It's good. So the second part of it is the profiles. I told you the shape. This is how we did the shape. Profiles are these profiles. They go from the core to the edge. For example, this is the density. At the edge, obviously, there's not much plasma. At the core is more. So you kind of go down here, and these are what the profiles look like. But as you see, I get these measurements. The red as our measurements with error bars. And I have these other diagnostics all around. I need to take all this diagnostics and convert and find my profile. And that turns out to be a very, very hard problem, because I'm basically fitting a nonlinear PDE and doing all sorts of weird stuff. So we spent years doing this using CAKE. It's a consistent automatic kinetic equilibrium. So what this does is, offline, I have a code that gives me the 1D profiles, given my diagnostics. Does all the work. As you might imagine, this is the hard part. This is the 99% of the work, is just taking this. So once you have this, then I can just do the basics surrogate modeling thing. So I have plasma here. I have all these diagnostics, real-time diagnostics, and all the stuff that I'm doing. I can take that and turn it into a neural net that takes all the signals, the measurements, and then converts it into profiles. That's great. So again, this is a surrogate. And it works really good, really well. So this is the reconstruction of the pressure and the current. So the old current looks like this. It doesn't go to zero. Oh, sorry. Just kind of hangs out here. And the real-time version of our system is shown in the purple. So it's able to get this. This got to be this current here and all that. That basically, if you solve the problem properly, you should get. So this is great, and I'll talk a bit about it as well. But then we do this Keras to C, which I'm hoping to get someone at Google to pick up. That makes the real-time code. This is running in real time in milliseconds. Perfect. So what is so interesting about this is that I can not only get the 1D profiles, but I can train my model the way I want to train it. And I can do all sorts of nice tricks with neural net. So let me go back here. So this is a physics model of sorts, right? I have a code. But I can have noise, and I can have some of the diagnostics here fail once in a while. If I were to write a code to how to invert and do this when some of the diagnostics fail, you need like a bunch of if and then statement. If this diagnostic fails, do this. If this channel fails, do that. If the noise goes above this, do that. Well, it turns out to be impossibly hard to do that because it's a exponentially growing chain. But instead, what I can do with the neural net training is I can put in noise here, random noises. I just basically sample different noise structures, and I can kill different diagnostics at each run of my surrogate training. And when I do that, the neural net by default learns how to handle the issues robustly. So the first time we turn this on, this is literally the first shot that we turn it on. This is the Thompson scattering. It looks very nice and smooth. It's not. This is basically the diagnostic failed. It's just flatlined. It's dead. So the neural net, though, doesn't care. It can measure the temperature that's supposed to be given by Thompson because it learned through the training that if it's flatlining, it ignores it and somehow finds other ways to reconstruct it. And literally the second shot, we have another diagnostic failing. This is a charge exchange. It measures the ions. The ions are not zero temperature, obviously, but our control and our system is able to find ion temperatures here very well. So what this tells is if you have a lot of noise and instabilities and so forth that you want to model and fix for, neural nets are the way to go because writing real code is impossible. Okay, so this is one more important use case. Okay, so that's kind of standardish.
Is the intuition here that the measurements are correlated and neural net can recover them approximately from these correlations?
Exactly. That is exactly right. And I'll come back to it in a second. Because we do have, when you're doing inversion, you need more diagnostics otherwise than necessary. Otherwise, you can't do the inversion, right? So we do have some redundancy, and it learns how to use that redundancy. Okay, right. And the ions are correlated to electrons and whatnot. Okay, but this is generally the case in many applications. Okay, so now this is the standard way of thinking, right? You have the physics-based model, the old system. You take these boxes of physics-based things and you make machine learning ways versions of this. I showed you that. That's the surrogates and whatnot. But if you're doing this, you're like, why am I doing this physics-based model? These are, people did this in the 70s, 80s because they didn't have anything better. They just wrote this codes. Why don't I just take this diagnostics and map it directly to what I want using machine learning? So this is kind of the new way of doing stuff. So I'll talk about how we're doing that one. So let's look at some ideas here. So we call this diagnostic to diagnostic. So first we wanted to see, we have to be robust to channel noise and loss, right? So let's say that I have here the diagnostic. This is the interferometer. I have 4 channels of it. So what if I lose one of the channels? Can I reconstruct that from the other ones? That's what you need for robustness. So we took 3 channels and trained a neural net to reconstruct the 4th one. This is the reconstructed versus the reality. This is the Fourier transform. And you see these modes popping up exactly at the same times and the same shapes and so forth. So this tells me that I can really recover if one of the signals channels fail. So one channel failing. So we said okay, well, this is great. So we got a bit more cocky. We said, okay, what if a whole diagnostic fail? Can I reconstruct that from another diagnostic? So I'm looking at here. One diagnostic is electron cyclotron emission. These green ones here. I have 40 of these, and then I have, but this measures the temperature, and I have 4 of these interferometers that measure the density. So they're not really, I mean, they're correlated in some way, but there's no physics that I can write to convert one to the other. But we said, okay, let's try to reconstruct the orange ones from the green ones. So you train your, neural net, and this is the measured versus the reconstructed diagnostics for the interferometer. So it's pretty much on top of each other. And when we looked at, we have a alpha and eigenmode predictor. It basically uses this to find a mode, and it shows that the reconstructed model, the reconstructed signal, is pretty much giving the same results as the original signal. So this is great. So it tells you if one of the diagnostics fail, we can use this methodology to reconstruct that if need be. So, okay, this is interesting, but what can you do with it? So, well, what you can do is you can say, okay, I have different diagnostics. They have different temporal resolution. They're looking at different physics. They have different spatial resolution. So, for example, one of them is looking at electrons. The other one is looking at ions. One is measuring interferometers, like integral of what's happening here. And we have point measurements. So we said, okay, what is the most exciting thing is finding the edge. We can't measure the edge at all. It's very hard to measure. We have this diagnostics that measures it every 10, 20 milliseconds. But we have other diagnostics that are megahertz that can measure the core and the integrals. So we said, okay, if we were to combine electrons and ions and other density, can we reconstruct this very low frequency diagnostic, but it's very good, to higher resolution? So super resolution of the low resolution diagnostic. So it's basically multimodal super resolution. So the idea is kind of simple. It's multimodal and it's super resolution. So you probably heard of super resolution going from 1K to 4K or something. This is multimodal version. All right, so how does this work? So I put in a bunch of different diagnostics these are high frequency diagnostics. And we have the diag-to-diag neural net that can give us this Thomson right at the edge that we wanted to find, which is about 50 kilohertz or something. This is wrong. It's about 10 hertz or something, 50 hertz, not 50 kilohertz. So, okay, I put this in. So this is the inputs. These are different diagnostics, and this is the measurement. And I try to match the measurement there. And I do it for different time slices, but then I can train in between how to do it in between the time slices and get to a megahertz version of this. So this is really nice. So I can go from low resolution to very high frequency. But then you say, is this even correct? Well, it's the R score is good, but we have to do a bit more than that. We have to look at other different things. We looked at that. So there's an event called ELM. This blip here is an ELM. And as you might imagine, we're not lucky enough to see this ELM with the diagnostics many, many times. So here's one. And we wanted to see if our megahertz version, this is a super resolution version of the diagnostics. And as you see, it sees this event all the time. It's supposed to have this drop when the event happens. So that's great. So, we did many tests like this. And now we can have the profile, like that's the edge to the core of the whole thing. And instead of having it every 20 milliseconds, I can have it every microsecond. And you see the profiles. This is when the ELM hits, and the ELM you can see the pedestal. This is kind of crashing, and then it builds up again. So I can have these profiles of what's happening at the edge, which we weren't able to do before at all. So you say, okay, I get this thing at the edge. What is that even supposed to do? You're wondering probably. There's a phenomena that we can't measure at the edge. We think there is a phenomena that we can measure at the edge. There are just tiny islands. These islands are like millimeter scale, tiny islands that obviously we couldn't measure. And there's one here, one there, and then there's a bigger one down here, but we have no diagnostics there. So these two islands are shown here. But when you have an island like that, these islands kind of flatten the profile. So basically, it connects these points to each other. So the temperature here becomes a temperature there becomes a temperature there, and the density and so forth. So we want to see this profile to see if there's an island like this. This is predicted for a long time, but no one's able to see it. So we used a super resolution, first try, first time, first phenomena that we looked at was this. And you can see this is the simulation of what we think will happen. So it flattens and it goes up. It flattens here, it flattens there. And we see the same thing happening on our super resolution. And this is, the first time we're able to use diagnostics to see this event. So there is no physics here. There is no like hands, smoothing of data or whatever. Just put the data and you see this phenomenon. So you can think about it backwards. You can just say, well, I can use this in astrophysics or in other areas. I just use that super resolution and look for physics events like this. And once I find a physics event, I can say, oh, this looks interesting, and go back and try to understand it. So this allows us to find new physics, even though the ideas here are simple, right? Okay, so now this is the analysis. We want to then predict the future.
Question
yes.
about the previous one.
This one.
The super resolution seems like it requires a lot of data. So do you have like testing? I mean, how do you collect so much data to get these very fine-grained details?
Okay, so first of all, when everyone asks about big data, I say for compared to the Googles of the world, we got no data.
Yeah.
So our whole database, the whole thing, is about a petabyte, and we don't even use that petabyte. We're basically on the terabyte. So it's not that much data. But what you do need is I can show a bit of it. So there has to be some. You have the gut feeling, right? You have to have a gut feeling about why this might work. So if it's like, if I'm trying to measure the weather and I'm looking at my clock, there is a correlation, right? But if I'm trying to measure the weather and I'm looking at the light in my bulb, that's not correlated. So you have to have some feeling about this. You can write the simplified equation. So I have some slides on this. I don't have it here. That there is this gigantically complicated PDEs that I can write about the physics of this. And you can show that, yeah, that PDE is coupled to that PDE. But I would never in my life be able to solve that, even write it down. But you know that there's got to be something there. So that's number one. So you have to have that. And then second, like you said, you need data. But the question then becomes how much data? And I think that's going to be obviously dependent on the thing. But what we found is that you don't need that much data. So a lot of the, I mean, at least in plasma and in a lot of the physics, physics kind of self-organize into some states, right? So it's like if you look at the galaxies and if you look at plasma, there's some sort of a self-dynamic that leads to some equilibrium states and whatnot. We don't understand it really how that happens, but it does happen. So the process is not known, but we do know that at the end, there's going to be some sort of correlation. And those states seem to be much smaller than what you can imagine in your mind about possible states that plasma and the galaxy might take. I don't know. I went on a big rant here, but
no, that's good. And so now, building off of that, is there appropriate intuition for this? That I see a bunch of points, and like I'm thinking the parallel in time numeric methods that just like coarsely solve a solution, and then fine grain kind of wash through it, because I'm seeing you could just run a simulation for the blue lines.
Yeah,
anchored by the black lines.
If we could, plasmas are impossible to simulate. I'll show a slide on this as well. If you could, that would be a perfect way to use this, right? So you can do a course and then fill in the blanks. I mean, your folks, well, I don't know, DeepMind is your folks, but they're kind of, they have a paper on using how to do coarse graining and so forth, like, staging and so forth. Yeah. So it does work for that kind of stuff.
But is that the right intuition? Because I'm seeing like much more complex dynamics in the blue than the black. So I'm trying to figure out, where does that come from? Like,
well, that comes from here. Maybe go back a slide more. That comes from here. So if I go back here, so you see that I have, this one is density related. Mm-hmm. It's basically integral the density from here to there. Okay. So it's an integral, so it has some information about the edge, but it's a meshed up of everything. And this one is magnetics. So magnetics is related to here. This is magnetics out here. So you will pick up some magnetic fluctuations if something is happening inside. So the point is that all of these will have some intuition. There's some correlation embedded in there at very high megahertz level, but I can't even imagine what that correlation can be written as. So then I say, well, I don't know it, but I'm just telling there is some correlation, and then say neural net can find me the correlation. So does that make a bit more sense?
I think so. And actually, I think I'm now noticing how the funny shapes would turn out. If you have the correlation and you have some high frequency signal you're getting at, you can infer what the other missing signal would be that's low frequency. And that's how you get these, much
exactly.
finer
This is what we're
granularity.
doing. So this is what we're doing. We're trying to predict the low frequency from this high. And then we say, well, if I can predict low frequency, maybe I can just let it do the whole in between as well. And it turns out to be that's good enough.
Yeah. So, and your anchor is a high frequency signal and the correlation.
That's right. High frequency correlation between the low frequency and a high. And then I say, how about I go from high to high? See what happens.
That helps a lot.
Okay, sorry, maybe I didn't explain it that well. Okay. All right. Let me kind of move on from this. But this is nice. I mean, this is the type of these simple ideas that kind of help you figure things out. We can then predict how the plasma is going to evolve, because I want to control at the end. If I want control, I want to predict the future. I want to predict the future. So for that, we take the historic data. This is the actuator history, plasma history. And then I put in future control, because control is in my hand. I can adjust my neutral beams. I can adjust my magnets and so forth. And then try to predict the future profile. So this is profile at t, and this is t plus 200 milliseconds, and that works out quite well. And this is a shot where I basically made a model of the whole tokamak. Right, this is a data model of the whole tokamak, and I'm running it now forward as if it's a PDE. So I start in the beginning. I turn on the beams. This is the beams going up, and when the beams go up, density goes up, temperature goes up. And this is the reality versus our prediction. And there's some error bars here. But it's nice, but there's not much happening here. If you look at a more interesting shots, for example, when I'm increasing and reducing the beams, I can see that I can predict that really well as well. So temperature is going down, pressure is going down. When I reduce it, and it goes up, and I get this quite well. So this is quite nice that we can have basically a model from data for the whole evolution. So now we want to do compare that and use with simulations. So maybe I can skip some of this. So there's basically a gigantic slew of simulation codes that couple to each other, and you can run them. And the idea is that if you're at the small machines here and you want to predict the big one, you're doing extrapolation. So maybe simulations are more informative than data. So we looked at that. So this is a paper that just came out. So what it turns out is it doesn't pass the hypothesis test. It doesn't pass the p-test. So the simulations do not give you better prediction than just the basic profile consistency. So you can not using any time, you just fit a log from the core to the edge, and it turns out the simulations are not any better. So this is kind of sad, but it is what it is. So basically, it's telling you simulations are not that useful. But they have some, extrapolation power, so we still want to use them. So we combine simulation and data. So basically, these are the data points we have. These are machines we have, and we want to go to ITER, which is way out here. And then how do we do that? We have all these codes, transports, and whatnot, and then we have data from multiple machines. We combine them to extrapolate. So to do this, we checked out a simple way of doing this. So what we said is we have data from one machine, Aztecs, AEG, and we have data from D3D, and we have simulations. So we combine all of them, but we only keep the low confinement shots on D3D. Then we try to predict the high confinement shots on D3D. So this would be like starting a new reactor. You have like initial tests, which are fine, and you want to increase your confinement as time goes by. And we said, okay, let's train some neural nets and see what happens. So what happens is that this is the final outcome of this. So there's all the different ways of training this. And it turns out that most of the information comes from own data, like own machine. even though you can use this whole different machine, it doesn't gain you that much, and simulations don't gain you that much either. And it turns out, because the simulations are not that good and the data is noisy, simple methods give you better results, simple weighing of the simulations versus data, than all this nonlinear stuff, because you end up overfitting. So what this tells you is, if your data is bad and noisy and your simulations are bad, just go to the most basic level, right? You don't want to do sophisticated stuff. And data is always the king. That's the other outcome of this. Okay, so then we want to predict events so that we can take precaution against them, like the disruptions and whatnot that I was saying about. So here's an example of this. I have this EC diagnostics here. This is the raw data. This is the clean data using neural nets. And this is some event. This is the toroidal alpha in eigen mode. So I see it's at the edge here. This is the amplitude. This is edge. This is core. It's kind of going to the core now, and it kind of dies off. So this is kind of the standard ML techniques to find a mode. I'm predicting an event, right? It's 0 or 1 or some distribution of that, and I can find the location of this. So this is working. That's great. So now I need to go to real-time implementation of this neural net I got. That's how do we do that? So first we wanted to, let me see if I have time here. What does the time look like? Okay, I have some time. We wanted to see what type of neural nets are the best for real-time compute. And we believe that reservoir computing networks are really good for this. So the reservoir, simplifying it very here, so you have this gigantic reservoir. So you train this random reservoir of connections. And it is all random weight, but you have to make this big. You have to make this quite big. And once you do that, then you can train the output layer as just a final linear, basically trained weights. So this is all pre-trained and kind of random, and this one is just a linear training of map from all these big reservoir items to the output. So the nice thing is, you can use this and retrain it by just using a linear operation. So this takes about a few minutes versus on the CPU versus 5 hours for an LSTM. And the nice thing is, because I can train this really fast, it's a linear regression, I can do it in real time. So we did this. So what we're seeing here is when I have data from a year, I can if I have data from years from 2013 to 2018, I'm trying to predict a new year, 2019, where there's new hardware and whatnot. I have not that good prediction. Errors are high. But if I include the new data, then I get much better prediction, right? But what I can do is I can feed the data as it's coming in, because normally you would run an experiment and find the data and retrain everything. So instead, what you can do is real-time train the data, just basically doing a linear regression in real time. So here you see the prediction that we were supposed to get, roughly. And this is the bad one. Basically, you're not able to do it because something new happened to the machine in that form. But every 500 milliseconds, we're retraining it. And when you retrain it, it's basically now able to predict that event correctly, because it's learning the new data and it's adapting to the better solution. Sorry, so lower was better here. I said it wrong. So I can adapt it in real time. So we can do this in 100 milliseconds. So this is great for fast adaptive control. So the next part is converting this to a real-time C code. You can make a gigantic library with all the if you have a Keras code, then try to put that in. But no one in their right mind will put a library with Python things in a real-time code that needs to be robust. So we developed this Keras. It takes Keras model and makes you a very clean C code, and this runs really fast. People have been using it a lot, and some Google folks were interested in this. Well, we see Keras as Google's, so maybe some people can take this over, because it's a lot of work for us to keep this whenever someone adds new capabilities to Keras. So this is of interest to people. So now we can do the control. All right, the first thing we did was look at an instability. So there is this edge burst. So you see this, rows of plasma coming in. They hit the wall. They basically come and hit the wall tiny bit here. Yeah, these are not like the whole plasma, but bursts of heat flux. And if you apply 3D perturbations, these 3D coils here, make the basically turn the torus into a bit of a French crawler, a bit, then you can stop these modes. They can just, you see, they're stationary. They're not hitting the wall. So this is how it works. I showed you about these blobs here. These are ELMS instabilities. And if you apply 3D perturbations, the blue one here, you can suppress it. There's no more of them here. And then you can go back out by turning the 3D perturbations off. But when you do that, what happens is when you increase the 3D perturbations, confinement is going down. This is sad. I have a sad face. But when we reduce the 3D perturbations, it's happy. You can get a much better confinement. So then we want to kind of adjust this and use the hysteresis. Basically, you can go into the suppression that's higher field than you can get out of it. So combining these, we can get much better solutions that are more confined. So here's the example. This is the confinement is going down because I'm increasing the 3D perturbations, but ELMS did go away. And then I go down a bit, my confinement goes up, but the ELMS come back, so I go up a bit, go down a bit, and in the end, I can get to the state where confinement is much higher and there are no ELMS. So this is kind of a simple explanation of what's going on there. We have a much sophisticated control that takes in the real-time signals. We have a physics model and a handmade control system, and it adjusts all the coils to get very high confinements. The confinement is basically coming back to where it started, and no ELMS. So we implemented it on 2 machines and achieved the highest confinements. This is the fusion gain versus H98, which is that confinement. And we achieved the highest confinement on both machines without the ELMS. And this is a big deal. I mean, this doesn't maybe look like a big deal to you, going from 2 to 2.5 or 0.4 to 0.5, but the fusion power goes to the power of 4 of this. So this would make your fusion reactor like, I don't know, like half as big or something. So then you can say, why am I just using the controller and measurements independently? Why don't I just combine them? And I can do that by just designing a reinforcement learning. So this is DeepMind's Alpha Star example. So here what we have is you can train the Alpha Star. Basically, it learns how to use the joystick to win the game. But how do we do this? We have a model. The model is the video game. It's a very good model. And you then adjust the controls, and reinforcement learning finds how to do that, right? So you need a cheap, accurate simulator, but we don't have that, like I said, in the plasma. So we use the data-based model that I showed you, I was showing where we can replay the database model. So then that's our model, a database model. And then we say, okay, reward is increased diffusion gain and no instabilities. So then I run this, and based on this rewards, you can get a reinforcement learning algorithm. And when we do that, so this is the measurements. There's all sorts of the measurements here, and the diagnostics are beams and electron-cyclotron heating. It's like a microwave heating the plasma, basically, magnets. And then this is the reinforcement learning system. And you basically steer the plasma on this hill away from the instability. And like in an uncontrolled shot, you get this tearing mode, destabilizes, and then you die. Plasma just dies, disrupted. But in the control shot, it says, oh, there's a stability limit, so I should go down. Oh, there's a stability limit there, I should go up. So it kind of adjusts this and then avoids disruption and goes to high confinement. So this is the result of that. This is the shot without control. And you see that it drops to 0. So it's basically a disruption. And with the control, we were able to achieve like highest confinement without instabilities. This was published in Nature. The other one was Nature Com. And so the system looks kind of like this. This is the instability fusion gain, and this is the instability regions. So this instability regions are computed in real time, obviously. So fusion gain, we want is high, but we don't want instability. So in real time, it's calculating these boundaries, and then it's kind of avoiding and threading the needle to go to the highest fusion gain without instabilities. So that's the visualization of this. This was done with collaboration with NVIDIA. So they made for the NVIDIA yearly event before the CEO came out, Jansen came out, they showed this video.
In paving the way towards unlimited clean energy for us all.
Stability here, and then we zap the instability. I don't know if it came out.
In paving the way towards unlimited clean energy for us all.
Yeah, so that was nice because we're able to show that you can use reinforcement learning and all that to do controls, and some folks at Google were doing this type of stuff. So large language models are quite in these days. Obviously, we use that for designing a co-pilot. So we did this when right now there's a bunch of companies that are doing the kind of stuff, but this was like a few months after ChatGPT came out. So the idea here is that we have the GPT model, and you have your siloed data. You can combine them to train a neural net that basically answers your questions using the large language model and your siloed data. So we put all sorts of papers, information about the discharges, experiments, and then we have the large language model. So we call it ChatD3D. That's the name of the machine. So you can ask questions and it answers them. So there's a bunch of questions here. It says, who should I select? The physics operator, and it says Al Hayat. Seems to be, very extensive experience, which is correct. These things are useful for someone who's new. Obviously, these large language models are, useful, but they're not like, they don't know more than the best people, but they know better than the first year starting out new employee, so they can help with that. So here's an example. How do you quantify tearing mode? And it's telling you that you need to use the Doppler scattering, cross-correlation scattering, and then use that to look at the spectrogram, etc. So this is very nice, correct result indeed. But this is kind of cute. But another thing that our collaborators do, this is the CMU folks, is uncertainty quantification. That's kind of big now these days. This was done a few years back. So they developed the uncertainty toolbox as part of this project, and this is the most used uncertainty quantification toolbox. So it's kind of a plug if you're interested in using uncertainty quantification. Just use, well, if you Google uncertainty toolbox, this is the first thing that comes up on GitHub, obviously. It's the most used one, and it can tell you about the systematic, like epistematic versus aleatoric uncertainty and so forth. So that's a plug for us. And for conclusions, I showed you that we can use reinforcement learning to avoid instabilities and achieve high performance in fusion. We can achieve the highest confinement without instabilities using machine learning. We did this on multiple machines. It came out in Nature Com. And we can do real-time, very high diagnostic recalculations. Basically, this is the diag to diag, doing multimodal super resolution. So these are, I think, good applications. There's a lot more stuff, but I think this gives you an idea of what we're doing these days with machine learning. On tokamak side, we do more on stellarators. Thank you very much.
Yeah, well, thank you very much. This is fascinating. One question that keeps coming up for me is the difficulty you've been having with simulations, which I'm trying to contrast with some of actually like NIF or so, those like DOE folks who've spent a lot of time on looking at hydrodynamic simulations, and they seem to be more positive. So I'm trying to get your opinion about this trade-off between data-driven versus equation-driven modeling for this domain.
Okay, so I have a low opinion, but I don't want to throw if you look at the literature, you will see comparison of simulations with one time slice or one experiment. We were the first ones I don't know why we ended up doing it, because we were trying to train these models and we're like, the simulations are not that great. So my students spent 4 years really getting all the simulations on the same setup and all that. and our co-authors are the writers of those codes. So we are not cheating. I wanted to make sure that the people who wrote the code, the main people, are co-authors, so that no one can complain that we're not doing it right. So these codes are very good to interpret what happens. So after the fact, you can go and tune your parameters, run them, I say like a postdoc in the loop simulation. So you have a postdoc who's spending a lot of time running, and then you get some matches that looks like it, and you say, aha, this is happening because electron temperature was too low in the core, right? So then you say, oh, I understood it. The simulations are useful. But if you want to do prediction of what's going to happen, that is a total different phenomenon, because then you have to really nail it. You can't just have a postdoc tuning things and, you know, doing scans and seeing what's going on. I mean, NIF people, I don't know, they probably showed you from Livermore. I mean, they got some results here and there. I've seen that. But again, you have to look at the usefulness of it. So as far as I know, they have codes and they do this data plus them as well. Did anyone use that to do anything on the machine? That's the real, you know, case, right? I'm an engineer. The question is, who's using it for what purpose? If you're using it for analysis, understanding of physics, it is useful. If you're using it to design an experiment, are they using it to design an experiment? Are they using it to control the experiment? The answer is no. Right? So it's a difference, I suppose, in how you would think about it.
So yeah, that makes sense. And then I guess what's missing, and to what extent is data filling in our understanding, just as a black box, versus inferring equations or whatever understandable stuff that may be useful in the future?
Yeah. So just to be clear, I have some friends who are at DeepMind who are trying to do the simulations. I send our papers to them. I say, look, it's not working. And they say, no, it's going to work. So my opinion is not the only one out there. I think mine is correct, right? But so what is missing is I don't think the path of writing Maxwell's equations and the Newton's equations and that equation and that equation and putting them together on a PDE, whatnot, and hoping that it works. That's just not going to happen. I don't think that's going to happen. It's not that we don't have enough PDEs or we don't have enough cells or grid resolution is low enough and all that stuff. Or compute. If we had the people just say, if I had 10 times the computer, 1 million times the computer. So my question sometimes becomes, let's say I got the perfect PDE that does all of this stuff. It even has like the quantum effects and everything. Okay, perfect. And say I will do that. Okay, so I need 10 to the 22 particles, each of them. They say, yeah, we'll do that. We can run. I'm like, so what is your initial condition? I asked them, so okay, what is your initial condition? They say, well, you know, what? I said, what is your boundary condition? Well, then you converted this gigantically impossible integration problem into a gigantically impossible initial condition finding problem. Because I don't know where my ions are at a given time. I don't know where the electrons are. I don't know the state of their, you know, are they in the excited state? Are they in the non-excited state? What is the boundary condition? What is the temperature at the wall at that point? And what is the carbon, you know, detachment level? It's impossible for them. So I think we have to, at some point, it's the same with understanding human interactions, right? So you have psychology and you have politics. You kind of, you know, say, okay, I'm not going to be able to make a model first, or physics-based model for this. You kind of simplify and just do broad models. Its complexity sometimes is just unavoidable. And even though we want to model and make a PDE that figures out if there's going to be a war in China in 10 years, I don't think anyone's going to be able to make that model, because how can you, you know, do the integration or whatnot? So it's similar to that in a way.
So no, that should make sense. And obviously that goes like the wholesale model people and the social dynamics people, they have exactly the same problems. So maybe perhaps the last one is the fact that you were able to get a functional model mostly from data and like do your refinement, find the correlations, suggests that there is a lower dimensional model that, I mean, what are you doing here? I mean, in the optimal system, you have some equations that you're scanning the space of possibilities to say like the state must be something like this in order to make sense. You're doing this with data somehow. So it seems like there is some model, equational or not, that is out there to be found.
That is right. I mean, there is some correct modeling. So basically, what you're saying is, I mean, what are we doing? We take in this case, terabytes of data and convert it into a neural net, right? We don't want to carry around a terabyte at each iteration of our code. So what you're saying is data is out there. Why don't the physicists make a better model of it? I'm a physicist as well, by the way. I wrote codes and whatnot. That is not a bad way of thinking about it. And the question then becomes, what type of an equation you're going to write? Are you going to write a PDE? So for a lot of these things, so okay, let's say I'm not going to, let's say the PDE doesn't work, or not the PDE, but type of PDEs that we write don't work. So, what do you put in? So there's a path. I'm just saying the path has to be more thinking outside of the first principle model setup to maybe we do that with weather, right? Okay, at the end of the day, there's a Navier-Stokes that you're solving, right? You're not avoiding that. But for subgrids and subconnections, you have these database models that you kind of put in there. So maybe we combined those data, but what I'm trying to say, I suppose, is data doesn't give you a coefficient of your PDE. It gives you a total different phenomenology connections. So you kind of have to be able to adapt to that. That's my take. Now we're going too deep into this. I'm not sure if I'm making a lot of correct statements, but that is my feel.
You're roughly describing physics-informed neural networks, which is they're trying so many different architectures that we don't know.
Yes, I have a bunch of friends that are doing it. I have, faculty there, my students being faculty there. Very hard indeed. It's not working. Things are not working, right? That's the reality is, if you're just trying to find a coefficient of your PDE, that just doesn't seem to be working that well.
Oh, yeah, you're thinking like just pure pins. Yeah, I'm thinking that one, as well as loss. You put conservation of mass into the loss function and a dozen other ways of constraining the dynamics.
I'm still looking. I haven't seen a good. If you have, I have not seen. Look, there's all the people doing it for simpler problems, right? Talking about plasma is like 100 times, 1,000 times harder than fluid.
Yeah.
How many successful good fluids machine learning applications are there for simulation? And one of the students that worked with me wrote a whole paper comparison of everything, and it's kind of in the review for the last year because they don't want to publish it. So his result was that if you normalize everything, the best gain they've had was the speed up of 4 to 8 times, and that's it. There was no other gain in. I mean, people have been writing about it for a long time. That doesn't mean it's not going to happen, but the progress, this is the thing, physics-based model progress with machine learning have been very slow, and I think there's a fundamental reason for a lot of this. That's my opinion. But we've been very good at database one, right? If you try to do database weather prediction, the world is your oyster. They can predict it better than anything else. But it just I think we're using the physics models a bit more than what they were intended to be. For a lot of stuff.
Yeah, that makes sense. Well, thank you very much. This is fascinating.
Well, thank you.